Welcome to this explainer on the Digital Signal Processing Lab. Today, we're going to bridge the gap between theoretical math and highly practical Python code. Why? To conquer one of the absolute most persistent problems out there in engineering and data science: real-world, messy, noisy data. I mean, if you've ever wondered how your smartphone perfectly isolates your voice in a crowded, noisy room, or how engineers manage to clean up completely distorted sensor readings, well, you're in the exact right place. So, let's dive right in and transform some of that chaos into clarity.
To do that, today's roadmap will take us through 6 key areas: real-world signal processing, isolating frequencies, clearing the static, feature extraction versus filtering, voice activity detection, and finally, we'll wrap up with future applications.
Starting off with Part 1, Real-World Signal Processing.
Let's establish some foundational tools, starting with the FIR low-pass filter. You can kind of think of a finite impulse response, or FIR, low-pass filter as a really strict bouncer at a nightclub. This bouncer exclusively lets the low-frequency bass right through the front doors, while completely blocking out the high-pitched treble. When we're writing our Python applications, we use this exact concept to block high-frequency noise or unwanted fast oscillating signals, which allows only that slow, smooth, low-frequency data to actually pass through to our final output.
Conversely, we have short-term energy, or STE. Now, if a filter is like our nightclub bouncer, short-term energy acts a lot more like a motion detector for sound. It's a classic feature extraction technique. By calculating the sum of squared samples within a very short time frame, we end up with a single energy value. And we can use that scalar value to definitively determine if a specific signal component, like human speech, for example, is actively present or if we're just staring at absolute silence.
Moving into Part 2, isolating frequencies, specifically looking at signal separation.
Imagine we're dealing with a really messy input signal. Mathematically, it's an addition of 3 distinct sine waves oscillating at 5, 10, and 15 Hz all jumbled together. But our goal is to extract only the 5 Hz signal. To pull this off, we feed that mixed signal right into a window-based FIR low-pass filter. And we set the cutoff frequency precisely at 7 Hz. Why 7? Well, because 7 sits right between 5 and 10. The filter basically lets the 5 Hz wave pass safely through to the output while completely destroying those 10 and 15 Hz components.
So how do we translate that theoretical concept into Python? First, we use NumPy to generate our time axis and those 3 sine waves at 5, 10, and 15 Hz using np.sine. And then we literally just add them together. Now to build our filter, we leverage scipy.signal.ferwin. We give it 51 taps, which is just the order of the filter, and we specify our 7 Hz cutoff using a Hanning window. Then we apply this newly built filter to our messy signal using signal.lfilter. When you plot this out, the initial input is a chaotic, jagged waveform. But after running it through the filter, the resulting signal is a beautifully smooth, isolated 5 Hz sine wave. And to prove it mathematically, if you check the frequency spectrum, the input has 3 distinct spikes at 5, 10, and 15. But after passing through our 7 Hz cutoff, those 10 and 15 Hz spikes are entirely wiped out. We successfully isolated our target.
Okay, Part 3, clearing the static, or denoising. Let's trace how code handles a much more common real-world problem, a pure signal corrupted by random noise. Say our baseline is a clean 5 Hz sine wave. We intentionally corrupt it by injecting uniform random noise using np.random.uniform. This creates a super jagged, noisy array that perfectly mimics real-world sensor interference. To clean this up, we design another FIR filter. But here is the absolutely critical engineering trick. Instead of just standard filtering, we use scipy.signal.filtfilt. This specific function performs zero-phase forward and backward filtering. Basically, it filters the data forward, flips it, and filters it backward. This guarantees that our clean signal doesn't awkwardly shift in time compared to the original wave. The output of that filtfilt function aggressively strips away the high-frequency uniform noise, and it wonderfully restores the smooth, rolling sine wave perfectly aligned in time with our original signal. It's really elegant.
Up next is Part 4, Feature Extraction versus Filtering.
Before we jump into detecting human speech, we really need to understand why simply cleaning a signal is not the same thing as classifying it. This is crucial. Digital filtering, like what we just did with the noisy sine wave, merely modifies a signal. It strips out unwanted frequencies to give you a cleaner, smoother version of the original audio, but it's still a complex wave at the end of the day. Feature extraction is a completely different beast. It takes a complex chunk of audio data and mathematically converts it into a single, straightforward scalar value, like an energy level. We have to do this because if we want to make a binary classification decision, like asking, hey, is someone talking right now, yes or no, we can't just look at a messy wave.
We need a definitive number to compare against the strict threshold.
That brings us to Part 5, Voice Activity Detection, or VAD.
Now we're going to build a VAD system in Python. This uses the exact same foundational logic your smartphone relies on to know when you've started speaking to a digital assistant. We'll execute 4 precise steps here. First, we define our sampling parameters, setting our sample rate to 8,000 Hz, which is the standard for narrowband speech. Second, we literally chop the continuous audio signal into tiny 20 millisecond frames and calculate the short-term energy for each of those frames. Third, we establish a classification threshold. We'll set it at 50% of the maximum energy. And finally, we'll plot out our binary results.
Let's break down exactly how this Python script builds our VAD results. After generating a simulated audio signal featuring 1 second of silence, 1 second of speech, and another second of silence, we dive into the framing. We calculate that a 20 millisecond frame at 8,000 Hz equals exactly 160 samples. So we slice our entire audio array into these 160 sample chunks. To get the short-term energy, we simply square every single sample in the frame and sum them up using np.sum frames squared axis equals 1. Next comes the actual detection. We define our threshold, let's call it ETH, as half of the maximum energy found in the entire signal. Then the real magic happens with this single line of code. VAD equals np.where E greater than ETH 10. Basically, if the energy is higher than our threshold, Python assigns a 1 for speech. If it's lower, it assigns a 0 for silence. Tracking this conceptually, the short-term energy flatlines near 0 during the silent periods, but it massively spikes up during the speech segment, clearly crossing our calculated threshold. So the final result is a perfect binary step function. It stays flat at silence, jumps instantly up to speech when the energy crosses the threshold, and drops perfectly back to silence when the speaking ends. We've literally just taught Python to listen to and categorize audio.
Which leads us nicely to Part 6, Future DSP Applications.
What's truly phenomenal here is that the simple principles of filtering and feature extraction are the exact mathematical foundation for solving massive, high-stakes problems out in the real world. The Python methodologies we just walked through are actively deployed in the field right now. For instance, industrial engineers track dangerous mechanical faults in massive factory machinery by constantly monitoring the RMS energy of vibration signals. This is a concept that's nearly identical to our short-term energy calculation. A sudden spike in that energy means a bearing is about to shatter. Over in the medical field, cardiologists use the zero crossing rate, which simply measures how often a signal changes sign, to detect lethal cardiac arrhythmias. A normal heartbeat is very low frequency, but a deadly ventricular fibrillation is chaotic and high frequency. That causes a massive spike in the zero crossing rate, which can instantly trigger a pacemaker's defibrillator. We can even map human vocal tracts for high-end biometric security using MFCCs or Mel-Frequency Cepstral coefficients to identify exactly who is speaking.
As we wrap up this explainer, it leaves us with a really fascinating engineering proposition to think about. If a few simple lines of Python calculating an energy threshold can so reliably isolate a human voice from absolute silence, how might these exact algorithms be scaled and deployed as adaptive filters? Could they redefine our ability to predict and prevent catastrophic mechanical or even biological failures before they ever happen? The tools to decode the world are literally right there at your fingertips.